Welcome everybody to the last video for week 1 of the class. And this video covers another concept that isn't so important in the class. It's more of kind of like an interesting application of circles and a relationship between something that we're all very familiar with, which is linear speed. I know how fast something is moving if you drive it, just a car in a straight line, for instance, and also how quickly something is moving, say, around a circle, and basically how quickly its angle is changing. And this, again, may not seem supremely interesting, but it's actually quite interesting. I'm going to try and illustrate it in the following fashion. So first off, we need to talk about, what is linear velocity. So definition. So linear velocity, well, actually, let's just define velocity. So velocity indicates the speed and the direction. Of an object's movement. Okay, so in 3D, I have to tell you what direction I'm going. If I just tell you I'm driving 5 miles an hour, but I don't tell you if I'm going left, right, up, down, sideways, whatever, that's pretty useless information. Now, in one dimension, what we're talking about is pretty much, we have a path, and maybe we have a car on it. And let me just draw my beautiful little car here. Let's see, what does a car look like? Kind of looks like something like this, right? All right, that's my car. If you don't like it, I hate you. All right, so that's my car, and it's moving one way or the other, right? Let's say it's moving to the right, and if right is positive direction, if saying that it's moving 5 miles per hour, positive 5 miles per hour means it's going to be moving to the right. But if I turn around and say that my car has a velocity of negative 5 miles per hour, that means my car is now moving in the negative direction. It is moving to the left. Okay, so that's what velocity is. And it basically just kind of indicates the speed and direction at which something is traveling. And we are all very familiar with this concept. If you drive a car, you're very familiar with it. If you've been driven in a car, you've been very familiar with it. Even if you don't, even if you just get around by walking, when we talk about linear velocity, this is what we're talking about. We're talking about an object's change in position with respect to time. Okay. Now, when we talk about this thing called angular velocity, so definition, angular velocity. Angular velocity, well, if linear velocity kind of describes at which at which your position changes in a straight line with respect to time, hence linear velocity. Angular velocity is the speed at which what is changing? Well, it's the speed at which your angle is changing. So angular velocity measures the speed and direction that an object's angle is changing if that object is moving on a circle. So that's the supposition we're going to make. If the object is moving in a circular path. Circular path. Now, you can have angular velocity and not be moving in a circular path, but because this section studies circles and their applications, we are going to just stick with the idea that we have a car that's moving in a circular path. Now, what is the relationship, the connection between the two of these? Well, let me pose you a question, okay? Let's pretend we have actually 2 circles, okay? Let's say we have the small one, and let's say we have a big one. And let's not make it too big. Let's try and keep them centered. Okay, so let's pretend that I have 2 cars, okay? I have one car that is on the green circle, and I have one car that is on the purple circle here, okay? And they both are hopefully lined up with, they're both lined up from the center. So did I do that right? Close enough. Okay. And let's say that both of the cars are moving in this direction. Okay. My question for you is, so my first question is, if the cars are moving, so maybe after some amount of time, this car is here. Maybe I'll draw my straight line first. So after some amount of time, the pink car is out there and the orange car is here, and so on and so forth. Right there, they're still moving in this direction. Okay. My question is, is the angular velocity different for the two cars? Is it different? Okay. Are their angles changing at different rates? Okay. And as a reminder, right, this is the angle at their first position. Maybe I'll call it theta 1, and maybe their angle after some time, that's theta 2, right? Is the angle that the cars are experiencing changing, and is it happening at different rates? Well, the answer is no, right? Clearly, they are both rotating at the same angular velocity. Okay, right? That makes a lot of sense. Now, my second question is, which car is, or rather, we'll say, has to cover more ground? Which car has to cover more ground in the same amount of time? In the same amount of time. And thus is moving faster. And thus, has a faster linear velocity. Has a higher linear velocity. Oops. Well, whatever. Okay, so which one does it have to be? Well, if you've ever ridden those rides where it kind of looks like this and you're a little kid and you get on it and all your friends spin you around and around and around and around, right? Where is the easiest place to survive that ride? Well, the easiest place for you to survive it is if you're standing like almost in the center of the wheel, because as it turns, you go pretty slowly, right? And where is the worst place to stand if your friends are spinning you in a circle? Well, the worst place to stand is literally standing right on the edge, because it just feels like you're going to get slung off, right? Because you are moving at the edge of the circle way faster than you are if you are moving closer, because you have to cover more ground in the same amount of time. Mathematically speaking, like, you have to be going faster if you're at the edge than you do if you're at the center, right? This is kind of an interesting paradox if you think about it too hard. But it's kind of the reason why time, if you live on the equator of the Earth, right? If maybe I'll draw like a little Earth here, right? If you live here versus living up here, right? Where are the days longer? Where are the days shorter? Well, what's the weather like? It's different here than it is up at the North Pole, because if you live on the equator, you're zooming around way faster, right? You're just going around and around and around way faster than the person all the way up at the North Pole. Okay, and so so the answer here for number 2 is the outer car. Okay, the outer car is clearly moving faster. All right, so now you might be saying, okay, well, if they both have the same angles, right? They both have the same angular velocity. How is it possible that the outer car is moving faster? Or maybe you subscribe to that idea. Maybe you're thinking, that, oh, well, it's believable, right? It's believable that the outer car is moving faster than the inner car. So what is the relationship between the two? Well, in order to find the relationship between the two, okay, the relationship between the two, relationship between linear and angular velocity uses a physics concept. And the concept is something you're all very familiar with, which is that distance equals velocity times time. Now, this concept should be pretty familiar if you've ever gone walking before, ridden a car. If I were to tell you that your velocity was equal to 60 miles per hour and your time was equal to 2 hours, then, this would give you that the distance that you have gone is going to be 60 miles per hour, times 2 hours. And these hour units are going to cancel, and they're going to leave you with a solution of 120 miles that you have traveled. Okay. Now, the goal is to relate linear and angular velocity. And so from that, we are going to use a second formula, and that formula is of the following nature. So we need to use this, and the formula that theta is equal to omega times time. Now, this omega here, I didn't explicitly tell you yet, but this omega here is, it's a Greek letter, and it just symbolizes our angular velocity. Okay, so this is our angular velocity variable. So why does this make sense? Because, for example, if I tell you that your angular velocity, your angle is changing at, let's say pi radians every hour, right? And then, your time, if I tell you that your time is equal to 2 hours, well, then, how far has your vehicle moved, right? How far has the angle changed? Well, this is just going to equal pi radians per hour times 2 hours. The units are, again, going to cancel. And this is going to leave us with 2 pi radians. Okay, so what does that mean pictorially? Looking at a picture, what this basically says, let's see if we can make a better circle. Okay, what this basically says is that, if your car were to start here, then if you are experiencing an angular velocity of pi radians per hour, that means in 1 hour you will have traveled, pi radians. So it should make sense that in 2 hours you have gone 2 pi radians, aka all the way around the circle, which is the answer that we got. So hopefully these equations make a little bit of intuitive sense. And our goal is to basically, figure out a relationship between our linear velocity v to our angular velocity omega. So what I'm going to do here is I'm just simply going to give you the equation, which is basically that the linear velocity, the speed at which the car is moving, is equal to the radius of your circle times the angular velocity. And it's going to be a homework problem for you to show this relationship. Show this relationship. Okay. And you can check out your homework for that assignment. So this is going to be the formula that relates the two. So if you ever have any questions and it's asking, if you have, say, a circle or a circular path, it might say, and that circle has a certain radius, if it wants to. So let's say it has a radius of 3 miles. And the angular velocity, the speed at which a car is rotating is, maybe it's 32 degrees or something like that, 32 degrees per second. And it's asking you, what is that in terms of linear velocity? You'll have to do some unit conversions, right? We need this angle to be in terms of radians. Okay, and we would also, we need other units or all of our units to line up, but eventually we will just very easily get our velocity in terms of whatever the appropriate units are. Okay, and so this is, again, angular velocity and linear velocity. It's not super important to the end result of this class. I'm not going to lie and pretend that you need to know it, perfectly or you're screwed, right? This is not one of those concepts, but it is something that your homework will be on, and so as such, something that you should know at least for this week. Okay, where should you put the primary focus? I would say your primary focus should be in learning those terminal points, understanding what the unit circle is, kind of getting familiar with the idea of using radians as a measure of movement, as a measure of an angle, because we are going to dive in headfirst into trig functions starting next week. All right, so that's going to do it for this video, and I will see you all in the next one.